But the viewer is not connected to the
Oh, February 4th.
You have to worry about it. This is a possible.
Oh yeah, it's not. It won't be like Thursday, such a thing. Yeah. Friday or something. Thursday, except for not to be public. You still need more napkins. No, there's like water everywhere. Good. Seeing Robert. That's true. Fright House is out. That's so weird. Night calm emoji? God. Están inundando. Oh, it's so it's more of it. I'm doing that all class. I just go like every minute. I was making this diagram. So hard not to like that. Oh, they can come.
Beautiful.
It's the maximum distance. It just goes translate.
Because my it was in the way.
How do I get work done? I just talk to the computer. here to talk to your clients. Actually, goes. This is the reaction. I just the vibrations like roll whatever. That's a whooping back and forth interesting. But one for the homies.
In those office hours during this class time. Is it okay if I go to it and you watch this lecture?
Of course. Sure. Yeah. That's why I post the recordings online.
Thank you so much, Professor. I appreciate it.
Yeah.
I'll be back for answers though.
Okay. All right.
So why are not like that? It might be.
Shoot, I didn't turn on the projector. That would be helpful for you guys. It's like something's different today. Sorry about that. Well, it's 4 o'clock, and so technically we're beginning now. But silly me, forgot to turn on the projector, so we're gonna wait a couple minutes for it to come up. There it is. All right. All right. Good afternoon, everyone. How's everyone doing today? Doing good. Doing good. All right. So I finished grading the midterms. I actually just finished right before I ate lunch today, and so you guys did really well. And so the average on the midterm was about 41.5. It shows a little bit higher on Canvas, but I calculated myself it's about 41.5. Canvas always does a little bit higher. Okay. And so of course I have them here today. And so if you're in class, you can come pick it up. But if you're not here, if you're on Zoom, I'll bring them to class on Tuesday as well. So you can pick them up then. Or just anytime you just catch me on campus, you can pick it up then. Okay. All right, so your grades are on Canvas, and you know, for those of you here, please pick them up and look over them. And so, you know, I always say this every time I return an exam. You know, I make mistakes grading. I don't try to make mistakes, but it happens. And so, you know, if you get your exam back and you look at the feedback and you see how many points you got, and you think that you know, you want to discuss your exam, you think you want to get more points, that's fine. I'm always happy to talk about those things. You know, just please do it in a timely manner. And so I think on the syllabus, I officially said a week, but with kind of how my schedule is this semester, you know, I'll give you guys a little more time, but don't wait until, you know, right before Christmas to ask for more points on midterm one. Okay. And so, because I want you to look at, I want you to see what you got, and I want you to just look at my comments. Okay. All right. And so that's midterm one. Okay. And so, you know, please come pick it up after the class today. Other announcement I have is member homework 4 is posted online. And if you haven't taken a look at it yet, I would definitely recommend taking a look. I don't think the problems take so super long to do, but they do kind of test a lot of, you know, fairly deep understanding of the next couple of weeks. And so, like I mentioned on Tuesday, it's good. It would be good for you to take a look at the assignment, kind of see what I'm going for in those questions, and then try to find that information in the lecture. I think you'll have a much better experience with the homework rather than watching all the lectures first and then trying to do the homeworks after that. Okay. Okay, and so that's all my announcements. So are there any questions I can answer before we get started for today? Okay, all right, and so the topic for today is we're going to continue on with our lecture notes on Gait biomechanics. And so last time we talked about walking, and so today, you know, I'm going to spend, there's just a little bit more about walking that I want to cover, and then we'll talk about running for the rest of the lecture today. All right, so I know I was a bit late turning this on, and so I'll give it maybe 30 more seconds for you to write down if you guys are still writing down the learning objectives. Okay, all right, so let's go ahead and get started. And the last topic I wanted to talk about in walking is kinematics. All right, and so kinematics, you know, hopefully that's a term that you're familiar with. Hopefully that's not the first time you're hearing it. But as we kind of start talking about human dynamics and human movement, you know, that's something that we're going to be talking about a lot. Okay, and so I'm going to go ahead and define the term first. Okay? So when I talk about kinematics from a biomechanical standpoint, specifically about human movement, basically what I'm referring to is the description of human movement using basically various measurements that we can obtain from the body. Okay, and so typically the way that we measure kinematics is we do it through body angles. Okay? Because anytime your body goes through any kind of motion, and so like, you know, imagine, I use this example a lot, but imagine, you know, picking up something off your desk. Okay, so your bicep is curling. And so, you know, let's say that your arm looks like this. Okay. And let's say that you're picking up an object. And so you pick up the object, you know, your arm might be in this kind of position here. This is the hand. This is the object. Okay. And then you lift it up into that position. Okay. And so to do that, one way that we can characterize that motion is if we measure this angle right here. So we call that angle theta. Okay. That angle theta is going to change from the first position to the second position. Okay. Okay. And so when we talk about kinematics, what we're talking about is measuring that angle theta over the course of time. Okay. Okay. And so we're going to be focusing a lot on body angles. And so maybe not next week, because next week we're talking about muscles again. But the week after that, when we start talking about actual measurement techniques, this is typically how we measure movement. Okay. And so just to kind of give you a preview, we'll be talking a little bit about motion capture in a couple of weeks. And so if you're familiar with motion capture, you've probably seen the suits of like the Pixar where they wear the big black suit and they have these little white balls on their suit, and they use that to track their movements. Well, that can actually be used in a scientific way as well. And the way that we translate that kind of raw data from the mocap suit to analysis is by tracking these body angles. Okay. And so that's what we mean by kinematics. And so kinematics, just in a general sense, is really just a way to describe motion. And so probably the first time you learned kinematics was from a physics class. And so in physics, you probably learned things like position, velocity, acceleration, right? These are all terms that we can use to describe motion. It's just that the way we do that in biomechanics is that instead of linear velocity, linear acceleration, we're using body angles, angular acceleration, angular velocity, things like that. Okay. All right, and so we can measure such things for the walking motion. And so when we measure the kinematics of walking motion, we're measuring in total 16 degrees of freedom. And so in total, that means there are 16 specific angles. And I think a couple of those are actually XY positions too. And so you kind of need to know the XY positions of certain central body points, like often the pelvis is used as kind of the central point. But then most of those are actually angles. And so those would be like the flexion angle of the knee. Those would be like the rotation angles of your hip joint. Okay? So, and remember, your hip is a ball and socket. So you need at least 3 angles for that. 3 angles for the left, 3 angles for the right. And your ankle also has several degrees of freedom as well. Okay. And so when we measure these, when we measure these kinematics, oftentimes we're going to get graphs that look like the following. Okay. And so let's say that the x-axis here is time, and the y-axis here will be this will be the hip flexion angle. Okay. And so we can measure this relative to certain events. And so, remember the walking cycle has certain events such as, heel down, toe off, things like that. And so the one event that I'll mark here is toe off. Okay. And so if you measure the hip flexion angle, then it might look something like this. So this is just an approximate graph. And so as you go through the walking motion here, okay, so your hip is going to be, have that certain angle, certain positive angle right there. And then once you're at toe off, that's when it comes up like this. Okay. All right, so let's do one that's a bit more easier to see. So let's do knee flexion angle. Okay. And so this is the angle that the knee makes. Okay, so the knee is pretty easy to visualize because the knee is basically a hinge. Okay, so there's only kind of one way for it to bend. And so once again, I'll go mark off the location, the time when toe off happens. Okay. And so of course, this one, I'm doing this for one full gait cycle. Okay. And so what this graph shows is what is the angle that the knee makes relative to the other limb as you go through one full gait cycle. Okay. All right, so what you see is that during the stance phase, so while your foot is on the ground, you're going to flex the knee a little bit. But then during the swing phase, when your foot is off the ground, that's when your knee is flexed and locked, right? Because we talked about last time that when your leg is swinging, then your knee has to flex to kind of make sure that your foot clears the ground. And so there's a period of time when the knee flexion angle goes down. But right when it comes off like this, that's when the knee flexion angle goes up. Okay. Let me draw a picture with this one because I think this one's a little bit easier to see. Right. And so what we're measuring here is the knee flexion angle. So if we kind of measure it just like that, okay. At this point right here, we're at toe off. Okay. And then mid swing right here, the knee kind of looks like this. Okay. And so in all these pictures, we're measuring this angle theta right here. Okay. All right, so these are two example curves right here. And so, when we talk about kinematics and I think later today we'll talk about the kinematics of running as well, what we're interested in really is the body angles, okay? And by body angles, I mean just the angles that two limbs make relative to each other at a joint. Right, so we'll be talking about this, not next week, but in the coming weeks, but I just want to introduce this to you here. Because again, walking is something that is kind of usually visualized. And so you can, see people walking all the time. And so if you think about it in terms of, how flexed or how, what angles that their limbs are making relative to each other, that's kind of the idea of kinematics that I want you guys to pick up from this. Okay. All right. Any questions on this? All right, and so that's it for walking, right? And so we spent the past lecture and 15 minutes talking about that. Let's talk about running. Okay, but before we go to running, we first have to talk about how we transition from walking to running. And that concept is called gait transition. All right, and so I think when most people think of running, they think of running as kind of a sped up version of walking, right? And so usually if you have to get somewhere more quickly, you run there as opposed to walk there, right? And so I think the way most people think of it is that, in order to transition from walking to running, you have to increase your walking speed. Okay? The way that we usually do that, well, there's a couple ways you can do it. And so one way that you can do is you can just simply take larger steps. And so, to get somewhere faster, if you maintain the same pace or the same cadence, you can just take larger steps. And so some people do that. But I think the more common way that people get from one place to another faster is by increasing their cadence. So by making sure they take steps more quickly. Okay? And so by increasing the cadence, you're going to alter the biomechanics a bit, because instead of instead of having a certain length of stance phase and certain length of swing phase, you're going to be altering that. And so generally speaking, as your cadence increases, the length of your stance phase will decrease. Okay, so normally when you're walking, if we measure the ground reaction forces, okay. Right. We know that a big characteristic of walking is that there's a certain length of time when both of your feet are on the ground, right? And so if we were to measure the ground reaction forces, and so let's say that this is the left foot right here. And then this is the right foot. There's a certain period of time here where both feet are on the ground. Okay, so remember, we call this double support. But if you increase the cadence, what's going to happen is that these peaks are going to get smaller, because your foot's going to spend less time on the ground. Okay, so you increase the cadence, your left foot might look like this. Your right foot might look like this. Okay. And so the amount of time of double support is going to go down. Okay. So intuitively, you would think that the way that we transition from walking to running is just to simply increase your cadence until that double support phase disappears, right? And so you just move your legs, you just keep moving your legs faster and faster and faster until you don't have any more double support. Okay. But in reality, the transition actually occurs before this. Okay. That is to say, if you're talking to someone and and they're not explicitly trying to speed walk, if they have to get somewhere faster, they're just going to start running, before they actually try to speed walk. Okay? And the reason for that is that after a certain point, if you're trying to maintain this walking gait, the walking kind of biomechanics, it starts to become very inefficient in terms of energy once you get past a certain speed. Okay? Okay. And for most people, on average, and so of course there's variation because people are different sizes, but once the walking speed has exceeded 1.5 meters per second, then it becomes more tiring to speed walk than it is to actually run. It is possible, of course, to walk at higher speeds than 1.5 meters per second, but then it becomes more of a chore to do so. Right? And if you need kind of evidence of this, next time you see someone walking across the street on a walking signal that lasts too short of a time, kind of see how they react. And so, generally speaking, when people have to get somewhere, and the speed that they have to use to get there is somewhere between walking and running, what they'll do is that instead of walking at a constant speed all the way across, what they do is they kind of run, walk, right? Because it's a lot more energy efficient to run for a certain time than be like, okay, I didn't really run, and then walk for a certain time and then speed up and run, rather than keeping one speed all through. Okay? And one of your homework problems is like this as well. And so in one of your homework problems, I asked you to compute, someone has to get somewhere in 15 minutes. And so, what's the speed that they have to achieve? And then what's the balance of walking and running that they should do in order to, get there in time, but also save the most energy. Okay. All right, any questions on this? All right, and so that's the transition. So let's talk about running now. And so first, let's start with the running gait cycle. Okay. And so, the reason we're talking about walking and running differently is that their biomechanics are actually quite different. Okay. So the most defining characteristic of walking is that double support phase. And so there's that period of time when both of your feet are on the ground. Okay. In running, we actually have the opposite. And so the kind of the most defining characteristic of the running gait cycle is what's called the flight phase. And as you can guess, just based on the name, the flight phase is what happens when neither of your feet are on the ground. Right, and so because we have this flight phase, it actually changes a lot of the biomechanics. All right, so let me draw out the cycle first, and then we'll talk about it. All right, so here's our timeline. All right, so just like before, I'm going to draw, the person running, and I'm going to highlight the foot that I'm going to highlight. Okay? And so this running gait cycle is for the right leg. Let me draw all the frames first, and then I'll draw what the right leg is doing. Okay. Draw this with dotted line too. Okay, and so I'm going to use red here to highlight the leg. Okay. Okay, so we're going to start at the left here, so that we're going to denote the start of the cycle as foot contact. right? And so the start of the cycle is going to be right when the foot touches the ground. Okay? But that's not going to last very long. And so the next stage here is going to be toe off. Okay, and so basically, as soon as your foot hits the ground, you're going to make a big step, and then you're almost going to jump off that foot, and that toe is going to come off. Okay, then you're going to have a phase, and so this is the flight phase that I was talking about, where neither foot's on the ground. Then your off foot's going to come down, and when your off foot comes down, your other leg here is going to be in what we call peak knee flexion. And then eventually that leg is going to swing forward, and then that foot's going to come down again, and we reset the cycle. Okay, and so this is going to right before foot contact again. Okay. And then of course the cycle is going to repeat. All right, so let's label the different parts of this diagram here and define all the stages of running. All right, so during this time here, when you have at least one foot on the ground, we call this the support phase. And so the support phase lasts for about 35% of the gait cycle. Okay. Then right after that, we have the flight phase where neither foot is on the ground. And so this is about 15%. And then right after the flight phase, the other foot touches the ground. So that'll be the other foot support phase. Okay? But I'm not going to label that here. And so, in the, you can imagine the next 35% would be the support phase for the other foot, and then the flight phase, and so on and so forth. Okay? We can make bigger. We can make bigger phases here. And so remember in in walking, whenever we had at least one foot on the ground, we called that or when the foot was on the ground, we call that the stance phase. Okay. And for this entire time after that, we can see the red foot is off the ground. So we call this the swing phase. Okay, so each foot is only going to be on the ground for about 35% of the time. So about a third of the time, it's going to be on the ground. Okay. All right. And so we just got done talking that the comfortable walk speed that most people like to walk at is about 1.5 meters per second. While the typical running speed that most people feel comfortable with is about 4 meters per second. We can characterize some of the other terms that we went over last time too. So the cadence for a typical person is about 180 steps per minute. And the typical step length is about 1.3 to 1.4 meters, okay? depending on how big the person's leg is. Okay? All right, any questions on the running gait cycle? I'm not going to redefine, all those terms, because all the terms we define for walking apply to here as well. And so things like cadence, step length, stride length, all those are the same. It's just that the numbers are a bit different because of running. Okay. Okay, and so the next thing we're going to talk about is ground reaction forces and the energetics. Okay. And so just like we did with walking, we can use a device in a lab called a force plate, and we can measure the ground reaction forces that occurred during running. Okay. And if you compare the ground reaction forces in running compared to walking, just probably as you imagine, the ground reaction forces in running are going to be a lot higher because you need to push off the ground a lot with a lot more force to accelerate your body, to accelerate your body forward. Okay. We can just plot it really quick. Okay, and so just like we did with walking, we can plot the vertical and horizontal components. So just like in walking, the vertical ground reaction forces are not going to sum up to zero. Okay, and so you have a net positive because there has to be a positive ground reaction force to oppose gravity. Okay. But just like we did with walking, we're going to assume that the horizontal ground reaction forces are going to add up to zero. Okay. And so once again, these are the ground reaction forces for steady state running. And so we're going to assume the speed doesn't change. And so the person is already kind of, kicked off and they're running now at a constant speed. So that's why the ground reaction forces are constant. Okay. All right, but what's more interesting, I think, is actually the energy, right? And so we spent a good deal of time on Tuesday talking about kind of this interchange between gravitational potential energy and kinetic energy, right? And so in fact, we said that when you're walking, these two entities kind of exchange with each other. And so there are certain times when your potential energy is high, and then there's certain times when your kinetic energy is high, okay? And that analogy was really important because then that allowed us to say that walking is very similar to a pendulum, okay? And then we kind of talked about that pendulum, I think, for the last 20 minutes of class. And so we're going to go through the same process here. And so we're going to take, we can take these ground reaction forces that are measured in a lab and integrate them to obtain gravitational potential energy and kinetic energy of running. Okay? Okay. And what you see here it's actually really interesting. And so at first it may not seem like much is different, but that small change actually makes a pretty big difference. Okay. So let's talk about potential energy first. And so let's say the potential energy might look something like this. Okay, remember potential energy is just the mass of the person multiplied by gravity. times the height of its center of mass. Okay, so we have mgy or mgh. Okay. And then kinetic energy. I'm gonna draw it offset just a little bit just to highlight it, but something like this. Okay. Right. Remember, the way that we measure kinetic energy is we take 1/2 times the mass times the forward velocity squared. Okay. Right. So both the potential energy and the kinetic energy kind of exhibit this oscillatory periodic behavior. Okay. So it's going to go up and down depending on what phase of the gait cycle that you're in during running. Okay. All right. So why is this important? And so, I said that, this, just by looking at these energies here, we can see that they're very different from walking, but, they look pretty similar, because if we go back up to walking, we still see that kind of oscillatory behavior. Okay. The big difference here is that these two energies are now in phase with each other. Whereas if we looked at the potential and kinetic energies in walking, they were out of phase. Okay? And what was significant about being out of phase was that, when two curves like this are out of phase, when one is peaking, the other is in its trough, and then the opposite is true too. And so you never have both peaking at the same time. Okay? And that's key because because if one is peaking when the other is waning, that means that the amount of energy that you have there is roughly constant, right? That energy is just being transferred between potential and kinetic energy. Okay? Here we don't have that, and so here what we have is that both the potential energy and kinetic energy are kind of peaking at the same time. Okay? And in fact, this peak here occurs in mid-flight. That means when you're running, you're going the fastest and you're the highest off the ground, kind of in that mid-flight. Okay? And so this means that the biomechanics, or what's happening underneath, kind of mechanically in running, is very different from walking. Okay? And so here's how we can explain running. Right? In running, we make a lot more use of the of your muscles to produce this kind of energetics. Okay? Right, so I've underlined the word actively there because your muscles are doing a lot more in running than they are in walking. Because in walking, your muscles are doing something, but they're basically just supporting your weight, and so they might as well just be a stick, honestly. And so so your muscles don't actually need to do much when you're walking, other than just support your weight. But in running, they're actually doing a lot more, and so your muscles are actually contracting and producing forces that are much higher than just your body weight. Okay. In fact, we can come up with a different analogy for this. And so instead of making the analogy of a pendulum, a better analogy for running would actually be like a spring or like a pogo stick. Okay. So let me draw the running person again. Okay. All right, so let me go ahead and draw the person kind of right before he's about to take off. And so this is right before toe off. Okay. So this is kind of right before the person's about to kind of spring off and go into flight. Okay. If we replace this leg right here, which is fairly compressed, and so the leg is kind of bent down. Okay. If we replace this with a spring, and so let's say that we have a spring that's kind of attached to the ground like this, and the spring is being compressed. Okay. Once that spring is released, that spring is going to release kind of all that energy and kind of help push forward. Okay. So of course, it's not just passive spring forces. Your muscles are kind of helping along with there too. But that's basically what's happening. And so when you're at kind of the valleys here of the energetics, okay, your speed is the lowest, but also your height is the lowest too. And so during this time, we can say that the spring is being compressed. And then after it kind of reaches its maximum compression and you're ready to push off, then all of that kind of elastic potential energy is released. And then that leads up to this kind of uphill right here. Okay? And then you go into flight, and then you kind of jump up, and your forward speed is the highest, and that's how it happens. Okay? Right. And so when you compare the biomechanics of walking and running, even though a lot of people might think that's just a logical progression from one to the other, biomechanically they're quite different in terms of what your muscles are doing, how much energy it takes, and how the different energies are coinciding within the body. Okay. All right, any questions on this? Okay, and so let's kind of run with this analogy, and then let's see what kinds of models that we can do, or what kinds of simple models that we can develop to kind of mimic running. Okay, and so some of the early attempts at modeling running was actually to make basically just a pogo stick, a robotic pogo stick. Okay, and so we call these hopping robots. And so these were first developed, and so I believe they were credited with the guy named Mark Reibert in the 1980s. Listen. And so if you looked at it, it basically just looks like a pogo stick with some weights attached to it. Okay? And so it looks something like this. And so you have basically a, you have your pogo stick. Okay. And then to kind of maintain balance, you had kind of this weighted stick that's on here. Okay? This stick was attached to a motor. And so that motor can modify the position of that stick, based on the position of the pogo stick, right? To maintain balance. And the way it moved was that, this pogo here kind of actively pushed off, right? And so it would push off like that. And so after it pushed off, the robot would leave the ground. Okay. And then while it was in the air, that's kind of like the swing phase of your running gait. The pogo stick would try to advance forward. And so the motor that's here on the balancing beam, that would try to rotate the robot this way. Okay. And so, I think a lot of the early people that saw this, saw a lot of similarities with how kangaroos move. And so if you look at how a kangaroo moves, they literally hop, from one place to the other. They don't kind of move both legs asynchronously like we do. And so this was very similar. And so it had only one leg, but it shared a lot of the same similarities. And so just like in running, when the robot was kind of right before it was about to take off, the robot would kind of crouch down and kind of build up potential energy in the pogo. And then when it was ready to kind of step, it would release all that energy and kind of move forward. Okay? And so it would come down, compress the spring, release it, swing forward, come down, compress the spring, release, spring forward, and so on and so forth. And it was able to actually make, forward progress. And it's actually pretty cool. And so, this was like this robot in particular is quite famous because, if you look up this guy, Mark Reibert, he actually became one of the big pioneering minds in the field. And so, after making this robot here, he thought, hey, I can make money off this. I can sell this to people. And so he was one of the founding members of Boston Dynamics, which is, as you know, is probably one of the leading companies in developing robots today. Okay. All right. All right, so let's. So I'm going to talk about another, pretty cool application here, which is the design of running tracks. Okay. And so for a long time, now we know a lot better because we've seen a lot of people get hurt. But for a long time, when you're designing, running tracks, and so tracks designed for people to run on, kind of the conventional wisdom was to make the tracks as hard as possible. So to make basic concrete tracks, because that will minimize the amount of time that you spend on the ground. Okay. Okay. Because generally, and this goes for other stuff too, the harder the surface is, the less time that you have to spend on that surface, right? And so just by the principle of impulse momentum, right? And so whenever you need to change, change direction of something, so you apply an impulse to it, a force over a period of time, if you increase the amount of force that you can generate, you minimize that time. Okay? And so the idea was to make a hard surface to kind of maximize the amount of force that the ground can put into your foot. And so that'll decrease the contact time and thus increase your performance, right? And so the idea was if you can make concrete tracks that are really hard, it's going to make people run faster, okay? Eventually we discovered that was not a good idea because people were getting hurt and they were getting shin splints and they actually weren't even running that much faster either. And so neither of those were a good thing. And so, nowadays, if you go to, a relatively well-designed running track, you'll probably see that it's probably made of this kind of somewhat squishy material, right? It's not exactly like foam, but it kind of has a little bit of give, right? And one of the reasons why we have that is to prevent injury. And so the idea is that if your foot's landing on something softer, then that's not going to drive as much force into your bones and your muscles and your joints, and it'll keep you healthier longer. But it actually increases your performance too. So actually, if you compare, let's say you try to run a mile on a track versus you try to run a mile on concrete on the street, you're probably going to run a little bit faster on the track. And there's some really interesting science behind that too. And what's fascinating about the people that discovered this, or the kind of the pioneers that discovered these kind of squishy tracks, was they used actually a very naive model. So I'm going to draw you their exact model that they use, and it's something that you can probably analyze with the pencil and paper here. Okay, and so what they found, or what they've noticed, from the biomechanics of running, is that the way people run is very similar to how a spring behaves. And so what they said was that, let's imagine that the leg is basically like a spring. Right? So let's say that this is their model for the leg. Okay. And so let's say they had just a mass. Okay. And so this mass here is meant to represent, the mass of the leg as well as the mass of the body that it supports. Okay. This mass is going to be supported by a spring. And we can estimate the spring constant for a leg, okay? Because at this time, scientists had already measured plots like this. And so if they can measure the potential energy and kinetic energy versus time, you can get a rough idea of what the spring constant for the leg would be, or the effective spring constant. Okay. This is probably the hardest part of the model, is that they also had a dash plot, and so they had a damping element to their model. Okay. Right. And so something like this should look familiar. So this is their whole model for the leg. Okay. It's nothing groundbreaking. It's basically just a damped oscillator. So that's something that you see in every vibrations class. You probably see it in like a class that teaches second order ODEs. Excuse me. Okay. And so based on the measurements that they were obtaining from the running, they were able to develop a model like this. Okay. And then what they hypothesized was that if this leg, so let's say this is the ground right here. Okay. If this leg were connected to another thing that also acts like a spring. Okay. And so in other words, if the track also had some kind of springiness to it, and so if it kind of acted like an elastic solid, then what they could do is that they could tune this. They can choose different materials for the track that had different levels of squishiness or different levels of springiness to kind of maximize the performance of this entire system. So this is actually, a problem that, you can solve this problem with just, MATLAB and, and a bag of Doritos or something, right? So by the time you finish your bag of Doritos, you'll solve this problem, okay? Of course, back then they didn't have MATLAB, and so, they had to solve this by paper. But all they basically did was, they formed, this system here is a damped oscillator. It had two governing ordinary differential equations. And then all they did was just test it for different values of K until they reached, a resonant frequency or basically a liftoff time that was optimal for the track that would beat what's in concrete. All right, and so what they found, luckily what they found was that, there wasn't just one track stiffness that worked. There was actually a range of track stiffnesses that worked. That was a lot softer than concrete, but then also a lot harder than gel. Okay. And if you're curious, what they found was that the optimal stiffness for the track was somewhere in the ballpark of 2.4 times the stiffness of the person's leg. Okay. That's kind of their approximate result. Okay. And so that's why, nowadays you don't see, really hard concrete tracks or asphalt tracks. And so if it's a running track designed for people to exercise on, to run on, it's going to be made of some squishy material. And that's, not only there to help prevent injuries, but also help you actually get better performance as well. Okay. All right, any questions on this? Okay. Oh, and of course, the type of shoes that you wear will help too. And so the type of shoes will also adjust your stiffness too. And so when you go buy a running shoe, part of the design process is to, to find out, what's the best stiffness for you to run on different types of surfaces. Okay. And so that's kind of part of what you're buying when you buy a running shoe as well. All right. And so the last thing I want to talk about before we close up today is the kinematics of running. All right, and so just like we talked about today, when we say kinematics of human motion, we're talking about the various body angles that the body undergoes when it goes through motion. Okay. Okay. So I think so like I mentioned earlier today, this field of just kind of measuring body movement has really benefited from kind of the last I would say 15, 20 years with the advent of motion capture. So before that, we kind of relied on kind of video and taking pictures at very high speeds. But now we can actually put trackers on a person's body to actually track their motion. In a few weeks, we'll actually talk about the science and the math of how that occurs. Okay. But, in the end, what you get are basic graphs that I showed you earlier. Okay? And so it's a little bit hard to show it, on kind of with just kind of handwritten notes like this. But kind of just like you imagine with the ground reaction forces, when you're running, the range of motions that your body undergoes are a lot higher than walking. And so let's look at the two same graphs that I showed earlier. So let's look at the hip flexion and the knee flexion. And I'll actually put numbers on these ones just so that you can see, how extreme these movements are during them. Okay. So this is time. This right here is angle. Right. And so down here we have 0%. So that's when the hip is basically, perfectly flat. And so by the hip, I mean, your thigh with respect to your pelvis. Okay. And the max hip flexion that we'll see here is about 70%. All right, and once again, this one entire curve right here is just going to be for one gait cycle. And so we're going to have a foot contact event on both sides. And our toe off is going to be somewhere kind of in between, kind of closer to the left side. Okay. All right, and so the kinematics kind of looks like this. So we kind of start kind of with a fairly high angle here when your foot first contacts the ground. And then it comes up and it goes down in a negative a little bit right after toe off. Okay. And then right when your toe comes off, then remember you're swinging your leg forward to make the next step. And so as you swing your leg forward, your hip has to flex quite a bit. And so hip has to come up just like this. And then we go just like. And so this kind of rapid increase here, this is from the swing forward. And this down here, this is the this kind of the push off or the gap, right? So remember what we said was running right before you push off, you kind of lower yourself and you kind of gather energy into your muscles, and then you push off right down there. And so this right here is kind of the gather, and right here is you have kind of the push off. Okay. Okay, so let's look at the same thing, but for the knee. Okay, so the knee flexion here looks very similar to walking, but of course the values here are going to be a lot higher. Okay, so we have foot contact, toe off. So knee flexion kind of looks like the following. The max here is about 140 degrees. Okay. And down here we have 0 degrees. Okay. Right, so in the first step, and so in the first stage, all the way up until toe off, remember this is the stance phase. Okay, so this is when your foot is on the ground. And so we have kind of a light load just like that. Okay. Your knee flexion kind of hits a minimum right before you push off. And then right when you push off, because you have to bend your knee quite a bit. And so you have to bend it in order to, during the swing phase, it comes back up here. And it wanes back down right when your foot's about to make contact with the ground again. Okay. again, this is just kind of an introduction to a lot of these ideas. And so, this past week here, we've talked about walking and running, and kind of what I hope you gain from this is that, it's kind of just an introduction to a lot of the really important ideas that are in dynamics rather than statics. Okay, so in statics, we talked about the human body in a certain way. We talked about joint reactions. We talked about muscle forces. Dynamics kind of almost plays by a different game. So, there's a lot more that goes on with motion than there is with statics. Okay, and what we talked about this week is kind of just a taste of kind of where we're going over the next few weeks. Okay. All right. Any final questions for today? Okay. All right. So I did want to end it a little bit early because I have the exams up here. And so if you're in class here, you can come pick it up. So I'm going to put them here on this table. I'm going to split them into 2 files just so 2 people can look at it at the same time, but you guys can talk and take it. Remember, the average on the exam was about 41.5. And so you guys did really well. So yeah. And so if you're on Zoom, you guys can come pick up the exams next Tuesday. So I'll bring the exams then. Or if you want to swing by my office anytime, I'll have them ready for you to pick up there. All right, so thank you everyone for coming today. Hope you guys enjoy your weekend, and I will see you guys on Tuesday. Hey, what's up? Probably this week 8, right? Probably talk about it next. So I'll talk. We'll talk first part of Tuesday. Yeah, because you guys need to form groups. And then
Yeah, we do.
Yeah, I'll start with this on Tuesday.
Do we even keep these exams?
Yeah, you can go. I couldn't. Some people stopped by this morning to pick them up, but I wasn't done grading it, so I wasn't giving them out yet. But now I put them all in the grade book and everything. So you guys can do it.
Will there be any like solutions posted?
Yes, yeah, I will. So I'll post the solutions. I'll post them tonight.
Yeah, I was ready to see and he screwed up. He almost went yes. He's the right state. But then he took the marker and he was like, whatever the
For the modeling of the leg, is there like a specific component of the leg that's the spring and one's the damper, or is it like?
They kind of lumped it all because your leg is just a mass of muscles and bones, and so they took kind of effective measurements, and so they kind of did like an inverse approach. And so they basically looked at measurements like this, and they said we can replicate these same measurements with a spring and a damper, and so these are kind of like effective components.
Okay. Cool. I'm just curious if like the bow is like spring, the muscle, damper.
No. They all kind of contribute to it.
Yeah. Okay. I don't know if you remember what I asked you during the exam, whether the position of the arrow will matter.
Yeah.
So you said here it's going to swing.
No. So the what I meant by this is that I said this is just a moment arm. And so the moment arm for this one, you kind of have to measure 2 different distances. So what I meant to say was that the LT should be first here, and then you need to subtract. So you do LT one this way, and then you do the LL cosine theta, and you can subtract that.
Yeah.
That's kind of what it's about.
Okay, but this one, the circle, this one's negative. So what I'm understanding is you want this force to rotate this way.
Yeah. So this force is going to kind of, this force here is going to produce a moment that goes that way. Everything else is.
Yeah, that's why I asked, because the arrow is here, so I thought, oh, closer to the joint, so it'd rotate that way.
Okay.
But
Okay. I
it
see.
didn't make sense in my head,
Uh-huh.
but that's why I asked you during.
Oh, I see. I see.
exam, so
I
was
think
like,
the way I interpret that question was I thought you meant if it was here, or that here.
yeah, if it was at the end of the foot here, I would have
Okay.
seen it go this way.
Oh, I see. I see. I see.
I thought because this was, I don't know,
I
I
see.
thought maybe in the
No, it
heel
was
it would
an angle.
rotate a little differently.
For that one, you kind of have to measure kind of, it would be like that if this distance, kind of put this foot on the other side.
You're doing
So
what?
if you compute this distance right here, and then just the horizontal component of this, but that's 70 degrees, so it's very
Yeah.
horizontal. You'll see it's still on the left side of that joint.
Okay, now I see it. This
Thank
is
you.
paying for this.
Good, what's up?
Just had a question.
And I was thinking it like it was an angle for
This was
here.
right when I wrote
I
it.
just kicked up.
Basically, when he was asking about why the whistles were short, I believe that was the question.
The moment.
That's
the moment.
I said the part was because they don't need to be long, the skeleton is the thing that provides the movement.
That's what I did.
So the main, so there were two things I was kind of looking for. I kind of gave credit for both. And so what I saw first was that you said that
right.
you
If
talked
I
about
did
the
like
form.
bring a sign.
Right.
So that's one of the main
Oh,
things.
you provided this is a
That
different
long moment, you have muscles that attach to you.
Yeah.
And that's biologically disadvantageous. That's that kind of hard, and I kind of assumed.
Oh,
That was the main thing.
And then for these, I was just curious, everything was correct except for the angles, I just kind of had the angles wrong.
Yes.
Oh, okay.
Have a good week. Thanks, you too.
Thank you.
Looking forward to this turning into midterm.
Hmm?
Looking forward to turning into this midterm. Trying to make it more